In this problem, we're asked to find RL for maximum power transfer and the maximum power transferred to RL. We're going to make use of the problem-solving strategy entitled Applying Thevenin's Theorem, and we need to do that because if you remember, the maximum power transfer theorem is based on if we have a Thevenin equivalent and we hook up a resistance RL, that RL equals R Thevenin for maximum power transfer. So our first step is to find the Thevenin equivalent. And remember, our problem solving strategy says remove our load. Well, our load is here, so we're going to remove RL. Then we'll calculate open circuit voltage, the Thevenin resistance, then we can use the maximum power transfer theorem. So for calculating the open circuit voltage, here's our circuit. We've now removed RL, and now we're going to go through and calculate. And if we look, let's use nodal analysis. I'm going to pick this node as a reference, and even though there's a node here, I'm not going to define a node voltage there. They really want to define their VOC. I'm going to define this node voltage as V1, and once I know V1, I can get V open circuit from voltage division across those two resistors. So if we apply Kirchhoff's current law at this node, we'll have V1 minus 12 over 3K plus V1 over 6K plus 2 milliamps equal to 0. And if we solve, for instance, we'll have V1 times 1 over 3K plus 1 over 6K is equal to 2 milliamps, and if you solve, we'll get V1 equal to 4 volts, and then by voltage division, VOC is 4 times 2K over 2K plus 4K, or it's 4/3 of a volt. Now we still need to find the Thevenin resistance so that we'll have our complete Thevenin equivalent. And if we look to calculate the Thevenin resistance, we can take this circuit, for instance, and turn the sources to 0. So if we turn a current source to 0, it becomes an open. If we turn a voltage source to 0, it becomes a short. So our resulting circuit for finding R Thevenin is here. And we note these two resistors are in series and they're in parallel with a 2K. So R Thevenin then is 7K times 2K over 7K plus 2K, and that's 14 over 9 kiloohms. So our Thevenin equivalent then is 4/3 of a volt, 14 over 9 kiloohms. For maximum power transfer, we want to set RL equal to 14 over 9 kiloohms. Let's define this voltage as V0, and by voltage division, V0 is going to be 1/2 of the open circuit voltage, so it's 2/3 of a volt. So the power dissipated in RL then is 2/3 of a volt squared divided by 14 over 9 kiloohms, and that's 0.2857 milliwatts.